there. Okay, I'm loading up the handout for this, and we'll go ahead and get rolling then. Here's hoping that I can pick the right computer. And we're up and rolling. Okay, so fluids and fluid dynamics, the biggest thing you can do, and we're about halfway into your studies at this point. And so it's with any lecture at this point, you need to start figuring how can it tie into the MCAT? In other words, how can you make bio examples? Thank you. So how can you make biological examples? So do we have any fluids in our body? Blood is a fluid. So what makes blood a fluid? What defines a fluid? Fluids are generally, most are compressible. The magnitude of compressibility can vary, but that's true because particles are not always touching. Sometimes they are, but it can move, exactly. So somebody put it in the thing. A gas and a liquid. Gas and a liquid are capable of flowing. So anything can flow when you apply a pressure difference. So do they flow from high to low or low to high in terms of pressure? Flow from a region of high pressure and low pressure. So a couple of things we can conclude. If we have a moving fluid, then we must have either A, applied a high pressure at one end, or B, applied a reduced pressure at the other end. And then the second statement we can assume, if the fluid is not flowing, what's true of the pressure? So if it flows from high to low pressure, if it's not flowing, there is no high and is no low. Pressure is uniform. And so we're going to go with that notion that a fluid can flow. So you mentioned blood. Is blood the only example of a fluid in our body? As I drink a little more fluid. So where else? Lungs, exactly. So what goes on in lungs? Oh, urine, good point. Lymph fluids, gastric fluids, perfect. But do the lungs also have a fluid? Sure, gas is a fluid. So it's easy to forget that. It's easy to ignore that, but it's a fluid, therefore it can flow. So explain to me how the heart works, or explain to me how the lungs work, either one. So in the case of the heart, do we generate a high pressure or low pressure? We have compression of the heart, perfect, generates a high pressure. It pushes blood out. But when it relaxes back to its original state, what happens? So there's diastolic pressure and systolic pressure. I don't know what the two of them are, so explain to me, what is systolic? What is diastolic? Perfect, resets. So systolic, when you have compression in the heart, degree pushes out through the aortic valve, starts to flow blood through the circulatory system. But when it expands back out, does it end up sucking blood back in? When the blood relaxes, or the heart, relaxes, the volume goes back up, does it create a reduced pressure that sucks blood into the heart? So it actually does both. So what causes blood to flow? Systolic, diastolic, or the pressure difference between the two? Pressure difference. Okay, I'm going to give you a set of numbers here, and you tell me if this seems reasonable. So systolic over diastolic for some patient is 108 over 72. Okay, sounds reasonable. In exercise, gosh, my C, I'm sorry, I'm just bothered by that. Let me make my C not look like that. So somebody explain me what this question is getting at. So let's say they tell you give you a data table with a whole bunch of patients. Let's say patient 17 has a resting blood pressure 108/72 systolic over diastolic. And when they exercise, which of these is a reasonable value for systolic, diastolic? So first off, when you exercise, do you need more or less blood flow? Need more blood flow, perfect. So therefore, you need to have a bigger or smaller difference between these two. Bigger difference. So right now, the difference between systolic and diastolic is 32, or 36, excuse me. So I'm going to make note of that. Delta equals 36. Let me write that better, sorry. So how's choice A looking? No change. It's still a difference of 36. That wouldn't help blood flow. Okay. What about choice D? Choice D, as in damn, also isn't working out. And then you're saying choice B, you want to get rid of? Okay, so I'm not sure why I would choose B over C, because this is 101, that's definitely increased. This is 47, 67, 71, definitely increased. They both would seem reasonable, but I mean, they're both awfully high systolic, but the bottom number. So what about that? Diastolic is not going to dip. Diastolic is going to go up just a hair. Systolic is going to go up substantially. So it's going to compress harder and going to relax to roughly the same point, but it's going to retain some of that additional systolic pressure throughout. So your best answer, do you agree, would be C. Did you answer that based on physics, physiology, or a combination of the two called physioics? Have to know my physioics, have to know how physiology and physics tie together. So I can solve this by Poiseuille's law, pressure difference equals flow, but I still had to know that the diastolic is going to go up ever so slightly. It's not going to drop. Okay, I'm feeling pretty good. I think I'm set on this. So I'm going to go ahead and click in the lecture then. And big picture, have to know how it applies to the body. You absolutely positively have to know the applications of it, blood flow and airflow. Both of them are going to play a role. Okay, so with that in mind, I want to start with the concept of what pressure is. So pressure is defined as force per area, but I want to give you a sentence and you tell me what I've missed. I know that pressure is force per area, but tell me which sounds right. I dropped something on my foot and I got a pressure fracture. I dropped something on my foot and I got a stress fracture. Which one sounds right? Stress fracture, perfect. I worry about my blood pressure being too high. I worry about my blood stress being too high. Blood pressure. What is the difference? Both stress and pressure are force per area, force distributed over a uniform area. What's the difference between pressure and stress? They're the same thing mathematically, force per area. Pressure deals with fluids, perfect. Stress deals with solids. So it's kind of interesting because just by those phrases sounding right or wrong to you, does that mean you actually knew that already? Did you already know that stress dealt with solids and pressure dealt with fluids because those sentences didn't sound right to you? And so one thing it's going to hopefully have you do is realize you know a lot of things without even being cognizant of knowing these things. So we're going to worry about fluids. Going to look at fluids from 4 perspectives. Stationary fluid, then we're going to put an object into a stationary fluid and consider the buoyant force. Then we're going to talk about a moving fluid, how fluid goes from one point to another, and then finally moving through a fluid, Bernoulli's effect. Everything we do today, I'm hopeful you will resort to real life examples to understand it and not equations. You can understand an awful lot more if you figure things out from perspective, from what you've seen going on in life. So if I gave you Poiseuille's law, let me just toss it out here. What's the first letter in the word volume flow rate? So if I want to measure how much volume is moving in unit time, the first letter in the phrase volume flow rate? That's right, Q. Excellent. Spell like a physicist. Volume flow rate, it will flow if there's a pressure difference. We came up with that. Oh, sorry, not to correct you, but I think what you were trying to write is was that physics spelling. I think you misspelled it, just so you know. And not to judge, not to point you out and make you feel bad, but yeah, you need to learn to spell physics spelling better. We're good. Okay, other things that matter then. Okay, so I want you to derive this equation for me from either math principles or deduce it from real life experience. How many of you have ever used a straw? Have any of you actually used a straw? Oh crap, there's two Z's in it. You're so right, sorry. So if you used a straw, did you create a pressure difference? Did you put your lips around it, make an airtight seal, expand your thoracic cavity, have an increase in volume, creating lower pressure? So you created a pressure difference. And what happened? Yeah, I'll work to improve. I'll be a better me tomorrow. Fluid went to your mouth. It flowed. Perfect. So it went up the straw. Was your straw about 8 feet long, or was it maybe just like, I don't know, half a foot, 2 inches long? How much did the fluid actually go up the straw? Really long distance or short distance? Very short distance. Would it be hard to use a longer straw? And how many have ever used a crazy straw? Those things are really long. Does it take forever for the fluid to get through? You use it for the fun, not for the satisfaction of thirst. You don't satiate thirst with it. You satiate these entertainment center. So where would you put length in this equation? Does length impact how much flows through the pipe? Do you think length belongs in this? Sure, we'll toss it in the bottom. Okay. Seems reasonable, put an L in there. Is it harder to drink a milkshake, water, tea? Are they all the same? Why is a milkshake harder to drink? Viscosity. What is viscosity? Ability to move. So I may not be able to give you any like physics equation for it, but I do know this. Ketchup, syrup, they are kind of hard to pour. Would you agree? They have very high viscosity. Thickness of fluid is a perfect way to think about it. So technically it's defined as the resistance for a fluid to flow. It's like liquid friction, for lack of a better phrase. But thickness of it, syrupiness, ketchupiness, all those things work because guess what? It's a conceptual test. That is the letter. It's an eta. I have no idea if I've written it right, but it's close enough. And does the area of the straw matter? For instance, if I used a boba straw, would I get more or less liquid satisfaction using a boba straw? Much more. Why? Wider. So I'm going to put a pi r squared. Okay. Do I have the key things in this equation, albeit maybe one of them is wrong, but at the very least, have I figured out where the things come from intuitively, and therefore I'd be better able to apply it? So this is how I want you to get all your equations. But does anyone want to point out something I may have gotten wrong? Not going to point out what, but maybe I got something wrong. No hints, but possibly I might have got something incorrect in there. Should be to the fourth. Okay. Reason for that. I'm a firm believer if you conceptually understand why, it's better. So the area thing is definitely true, but there's a second factor. if I consider two pipes, pipe 1 and pipe 2, how many learn fluid flows the fastest in the very center? So fluid in the center is going to flow the fastest. Okay, so there's friction on the edges. It's called a boundary layer. And as you move further in, it goes faster. So where's it going to be faster? A little bit from the edge or a lot from the edge? A lot, meaning I'm going to go on a limb and say if that's R, then if I drew that same R on this one, let's say that's R right there. Would most of you agree this entire center right here is a fluid going to flow even faster than the fastest point here? Which means is a good amount of this pipe having liquid go at a faster rate than this one, meaning it's not only wider, but it's also moving at a higher average speed. The particles travel higher speed, goes faster. As a result, this is a 4, and there's an 8. So the speed difference is R squared over 8. That's where it comes from. I don't care too much about that. What I care about is the following. Are there 4 variables that can screw with how fast the fluid gets through a pipe? Which means, can you tell me all about heart conditions and circulatory disorders based on 4 possible issues? So a weird question, but give me any sort of issue somebody has with their circulatory system and explain it in terms of these variables. So give me any circulatory disorder you can think of. Okay, so how many have learned about that? How many learned that as plaque builds up on an interior of an artery, the radius goes down? Is that a big deal or a small deal, Stephanie? Is that one of those things that, so what, who cares? Or is that actually potentially really harmful? Why is it such a big deal? Because it's to the 4th. A little bit of plaque buildup slows down the blood flow substantially. To compensate for the Q, we have to have an extremely high pressure. Yes and no. So excellent question. Would you need to calculate it outright? Hell no. But would they say if the radius went down by this amount, how much would the flow rate go down? That's reasonable. So if we cut the radius in half, the volume flow rate would go down by a factor of 16. That kind of math relationship, yeah, that's reasonable as far as the math goes, how one variable relates to the next. But no way would they say, given this, 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 and this, solve for this. MCAT's not about just crazy math. They're about comparisons. Yep, everybody, okay, oh yeah, it's private. So do you mind if I share that with everybody? Is that why boreholes are drilled to relieve pressure buildup of blood? Yep. Yeah, basically, it gives it another passage, gives it another way out. What does a stent do? I love that. And I want to ask that honest thing, because somebody just mentioned Grey's Anatomy is helping out. So when I first started teaching MCAT, there was a show called When I was a kid, it was just E, but then there was And honest answer, how many actually got into medicine because of TV shows? It just further added to your experience. Because when became popular, our class shot up, our popularity. And actually one of our teachers was one of the set experts for That was his side job. Our bio teacher actually ultimately took that job over ours after a couple of years because he was in charge of making sure that it was a realistic one. Yeah, Scrubs is going house. I mean, these shows, they definitely influence us. And lo and behold, you learn something. I'm pretty sure I'm a lawyer based on the amount of Law and Order I've watched over the years. Oh, interesting. I didn't know that about you, Lori. Oh, so but if you're SVU, then you're also a sociologist and also an expert in psychology of bad people. I'm just strictly a lawyer. I'm the regular one. So, yep. Okay. So yeah, somebody mentioned a Dr. G, somebody mentioned Grey's Anatomy. It is interesting because these are the kind of things where we get exposed to it. And I'm telling you, it may sound crazy, but understanding what happens in these episodes is not so far-fetched, including, I know Scrubs is a comedy, but again, just the crew people who work on it actually are in the medical field. They find the crazy ones. So, I mean, when you rotate through the ER, I'm sure you'll see all sorts of crazy things. Okay, so with that in mind, these disorders you talk about, yeah, this is why we do the things we do. So big picture, every equation you get, you have to be able to correlate it to bio. Q, as you learned it in physiology, how many learned that stroke volume times heart rate equaled some term that they gave that sometimes they refer to as Q, how much blood moves in a certain amount of time? So what is that term? Where you multiply the heart rate times the stroke volume. Cardiac output, perfect. George, why am I reading? Oh, somebody just put it up there, but yeah, cardiac output is also known as Poiseuille's law. Hopefully that seems okay. So if this seems clear, and again, this is main reason that I'm going to focus on how we do this stuff in terms of real life is because how many understand this equation much better because you can apply it to physiology than you could as a memorized formula. I'm so sorry. I've gotten you guys so off track. This is so bad on my part. Yeah, so this question always pops up. Anytime, and I swear, anytime you see in an answer explanation that blood is not an ideal fluid, so blah, 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 stop reading that information. Throw it away. As far as the MCAT's concerned, they treat blood like an ideal fluid. They don't, there's no BSing like that. It's glorified water. Now we know because of the incompressibility or reduced compressibility of some of the chunklets in the blood, the platelets and cells and some other things, we know that it has some non-compliant so that it's not perfect. But for our purposes on the MCAT, blood is just basically thicker water. So treat it that way. Anyway, yeah, there's going to be a new section. Get rid of the psych social and just having Grey's Anatomy episodes. Yeah, that they're starting that next year, in fact. So if you want to hold on. Okay, so I'm going to get rid of this. Going to get the stationary fluids. Going to get zeroed on. Here it comes. Okay, just want to get rid of this. This is going to pop up down the road, but just wanted to, the whole point. So I haven't really started in the core lecture, but want you to say to yourself, the equations are for relating variables, and I have to know them conceptually. Do not memorize. I'm sorry, time out. Don't derive, memorize intuitively how things fit. If I want higher blood flow, higher blood pressure, wider arteries, less viscous blood, be short.
Can I hop on and ask a question really quickly?
Please do, yeah.
So I remember a while ago when I was studying, like not seriously, I came across a document that had like 5 physics equations that had like, I don't know what they were equating to, but it talked about how like if you can figure out what variable is missing like in the question stem, then you use one of those core 5 equations. Do you know what I'm talking about by chance? And like
translational motion, yeah, that's something I wrote ages ago.
Is that something that we can touch on? Like, obviously not today because that's off topic, but I wanted to ask before I forgot about it. Is that something we could talk about, like, in depth of how to do those equations and figure out?
Most definitely, yeah. It's called the is it that method, and yeah, awesome. Definitely that'll fit in. But it's along the same lines here. If you know the variables, there's 2 questions they can ask you. Question number 1: if one thing changes, how does the other thing have to change to keep something else constant? That's one option. Or number 2, given this, this, and this, what is true of this value to keep this at a certain rate? So if this goes up and this goes up, does L have to change to keep Q constant? Those sorts of questions. So yeah, I mean, I'm going to try to mop up and toss in everything. And basically time is going to be our friend, I think. But anyway, let me go ahead and I'm going to erase this and then get into the core part of it. So, okay. So stationary fluids just sitting still, force per area. And so you again have experienced this in real life, because how many of you have ever gone into a swimming pool and swam to the bottom? How many have ever gone to the bottom of the deep end? Okay, for any of you who've done this, would you agree it felt weird? It felt something. What did you feel? What did you sense? Okay, it does feel kind of good, but high pressure. How many felt it on your sinuses, your ears, all the pockets of air in your body? Why didn't you feel it on your lungs as much? Your lungs didn't feel crushed, but how many agree your sinuses, your ears in particular? Yep. Partly holding your breath, but you're also holding air in your ears. Main reason, your thoracic cavity, your protective cage. Can the pressure of the surrounding water crush your rib cage, or is your thoracic cavity pretty much locked into its shape? Yeah, hopefully not. If it can, not a good thing. You're not in this lecture at this point. So nothing is compressing. The water is pushing on our rib cage, but it's not actually compressing our pleural sac. But is there any coat of armor, bone layer, that's protecting our ear canal? Nope. So therefore, can the water push in against it, against that membrane, and literally push it in and compress? Sure. Just out of curiosity, why do we have earwax? Because we're flawed. Yeah, it's just something to pick at. No, why? So we can mine for gold. I don't know why I asked, but yeah, unfortunately, I got to admit, I'm thinking all the same things you're saying, except for, yeah, the right answer. Exactly. We're waterproof. It's for moments like that. So water doesn't leak into us. It's basically a protective layer. So wax resists water. Thin layer of wax prevents water from actually leaking into our ear canal. Doesn't work well for all of us, but it's close. No. So really good question. So scuba diving, for whatever reason, was an obsession with test writers a few years back. So in the pool, you can run into it. But thing you do when you scuba dive, you pinch your nose and you exhale, blowing air from your sinuses back into your ear canal. They're all sort of connected, hence ENT, ears, nose, throat. There's all some sort of gas release. So by exhaling in and filling up higher pressure inside your ears, you offset that water pressure. So as water pressure outside goes up, you blow up your ear canals. So has anybody ever scuba dived and done that? Pressurized your ears? Just like when you go to the mountains, you yawn to release air out of your ears? So we adjust naturally. Underwater, it hurts like crazy. If you're scuba diving, you're down there for a while, you want to balance your pressure out. It's actually one of the things that they teach you to do really early, because the stabbing pain in your ear apparently is not as much fun as it shows on the brochures. Okay, so I ask you this. Is there any correlation between pressure and depth when you go into a tank of water? So do you feel the pressure near the surface or the deeper you go? Deeper you go, perfect. So we're gonna come up with something called gauge pressure. And again, I don't want to derive things, even though I'm about to. But gauge pressure is basically what you would read on a gauge if you went underwater. So we call atmospheric pressure 0, and everything is related accordingly. So plural, like not plurals in more than one, but plural is in your pleural cavity. when they talk about pleural pressure, they're talking about gauge pressure, what it is compared to atmosphere. So have you ever heard of positive and negative pleural pressure? Yeah, I haven't explained what gauge pressure is yet. I want to go back to pleural pressure real quick, and we're going to go into gauge. So what does it happens when your lungs have a so-called positive pleural pressure? Meaning you took a deep breath, air filled your lungs, and then when your thoracic cavity relaxed, your diaphragm relaxed, your pleural cavity got smaller again. What happened to the pressure inside your lung as it relaxed? Positive pressure inside. So there's always a pressure, but what that means is it's greater than atmosphere. So we call it exhaling. That's what's known as a positive gauge pressure. So gauge pressure is relative to the environment. So gauge pressure is your difference between atmosphere and what the pressure you're feeling, meaning it's what it would read on a gauge. So when you exhale, gauge pressure will be positive. When you inhale, gauge pressure will be negative. So pleural pressure in physio is the same thing as gauge pressure in physics. We measure them using different tools, but they're still the same thing. Okay, so you mentioned that H matters, the depth. Okay, being on Earth helps. I want to do a little bit of math. Weight per area is what we're dealing with here. So if I instead did volume, multiply top and bottom by H, then I'm going to get mgh, there's H. What is A times H, area times height? Volume, mass per volume is density. How many have you seen this equation before? Oh, there I go. I think I'm a physicist because I'm boxing things. So again, I apologize. Whenever I do physics, it's that nervous habit. I got to box it because suddenly it makes me a physicist. So, but gauge pressure, first of the few equations we'll have here. The deeper you go into a fluid, as H goes up, gauge pressure is going to go up. Okay, makes sense. So we have a tube here. I think we fill it with water, right? Or do we fill it with some other material typically? So when we use a thermometer, we usually use water, and a barometer, usually water, and manometers, all these things we use water, right? What? We use mercury? Why? It's shiny. Shiny is always good. I'll give you that one. But why do they use mercury, whoever they are, the people who invent things? Couple reasons. Number one, density of mercury is high or low? No. Not really sure. So got a couple high votes, couple low. No, gauge pressure is not the pressure of the inside. Gauge pressure is the difference between atmospheric pressure and whatever you're measuring. So think of it. What is a gauge? So when we say like your car has gauges, sometimes watches will have gauges. What is a gauge? It's a tool that measures. So yeah, the word gauge. So if I have a gauge on anything, like, don't you have a fuel gauge in your car? I mean, at some point, you want to know when the car is running out of gasoline, when you're empty. Yeah. So no, but gauge. The word gauge is that which measures. Your fuel gauge in your car is that thing you look at to see if it's empty, full, or somewhere between. So you've never heard the term to gauge your progress, to gauge something, to measure something. And I'm trying to dig this out of some everyday language. And so we use it to gauge how I'm doing, to gauge my progress. It's simply a measuring tool. A gauge is something that measures pressure. So when I'm sitting here in atmosphere, I feel natural. I feel I'm used to this pressure. I'm going to call this zero. Gauge pressure is any difference in pressure from atmospheric. So just like in lab, in GChem or OChem, did they ever tell you to tare the balance, T-A-R-E, to tare it? Okay, what does that mean, to tare a balance? Zero it out. Punch it so that anything that's on there, the weighing paper, the weighing cup, the beaker, whatever it is, you're not counting that weight anymore. So anything that goes in there is the difference between that being called zero. That would be a gauge weight, if you will, the weight of whatever you added beyond what is normally there. So what we're doing here, gauge pressure is just anything different from atmosphere. So if the atmospheric pressure is 1 atmosphere and something, you feel 2 atmospheres of pressure, you'd have a gauge pressure of 1. Yeah, it's a term just to measure relative to your values, surroundings. Like pleural pressure, again, is a gauge pressure of the lung. Okay, so with that in mind, getting back to this, we use mercury because mercury has a very high density. So because mercury has a really high density, does that mean I can measure pretty high pressures without having a restrictive height? If I used water, it'd have to go up to 32 feet to measure 1 atmosphere of pressure. But if I use mercury, it's about 76 centimeters. It's basically 2.5 feet or so. So it just ends up being a lot easier to use mercury. Second reason, is gas soluble in mercury? Can it escape? Or is mercury pretty much going to not let any gas flow through it? Won't let it flow through, so you can make a closed system here by adding mercury here. Okay, so here's what we mean by height difference. The gas here is pushing down the mercury, causing mercury to rise up to here. This is my equal height. So I'm going to tell you it's equal pressure here and here because it's not flowing. It's not going that way, it's not going this way. So the gas pressure pushing down this way must equal atmospheric pressure plus rho GH the other way, meaning air plus this mercury pushing right here to try to move the fluid that way equals the gas pushing back this way. Because it is stationary, pressures are equal. That's Pascal's principle. If there's no difference in pressure, there is no motion. So we have this then. Let me erase what I've written in red because it just popped up in a prettier computer generated form. So we have atmospheric pressure here plus rho GH. So the pressure of the gas pushing down at this point equals this sum pushing that way. Okay, so again, gauge pressure is the difference between atmosphere and what we get. So if I read the gauge, so if I looked at this gas and read the gauge pressure, that's the difference between atmosphere. I'd have to add it to atmosphere to figure out what the true pressure is. Okay, I'm gonna just hang on that question for the time being. Terms we have to know. Because mercury is such a common material in these devices, we have an entire unit dedicated to it. So 1 torricelli, is the amount of pressure you must apply to raise mercury by 1 millimeter. Is this one programmed into you from GChem? How many 760 torr per atmosphere is just so common from the things you did in GChem and gases that you couldn't forget it if you tried? And how many have tried? In fact, how many have succeeded and forgotten it? Okay, well, okay. So 3 of you have said you did. So much for that theory. But yeah, now hopefully you'll remember it. Hang on to it till January. Forget it the day after your MCAT. Isn't it weird, stupid things we just remember? Sorry to go off on that tangent, but yeah, I think I've already confessed. State capitals are so stuck in my head, although I thank goodness I've started to get rid of a few of them. But yep, Avogadro's, all those numbers get programmed in your head and you just hang on to them for whatever reason. So we are who we are. But that number you just gave me is kind of useful. I need to know this because these are GChem numbers. This is kind of what we use in physics. The bar has shown up so many times on the MCAT compared to real life. How many don't remember the bar other than where you went after your midterm? That's about the only time it ever showed up. So a bar is basically almost an atmosphere. So if you get any passage on the MCAT that says 2 bar, 3 bar, 4 bar, just substitute atmosphere for it. Don't waste time stressing about this unit. The Pascal, yeah, probably will show up in physics. Milliliter mercury and torr, definitely. the units that show up, the atmosphere, by all means. The bar, it may show up in the test. It's just there to screw with you. And so if you ever look at your car tire, it might even tell you, make the pressure 1.4 bar or something like that. So that is what it is. Okay. Let me get rid of what I've written here because I'm going to box it here because I like boxing things. So here's what I have in this system. I have what's known as a manometer, similar to barometer. Barometer measures atmosphere compared to a vacuum. This one measures atmosphere compared to a closed system. So this valve up here is closed. This valve here is open, which means, is the gas inside free to migrate in? I'm going to tell you that atmospheric pressure is 761 torr. So we're somewhere slightly below sea level doing our experiment. And that the internal pressure here is 682 torr. Do you believe me? Telling you the truth or lying as always? Why don't you believe me? Besides the fact that I lie 75% of the time, so it's bad odds to believe me. It's being pushed. How do you recognize that? What are you seeing that I'm not seeing? The height difference right there. So because of this height difference, you agree the pressure in here must be greater than 761. So if I told you the pressure inside here was 789 torr, then how high is that? So if I told you atmosphere is 761, internal pressure was 789, how tall is that? How high is that? "28 millimeters." Perfect. Excellent answer. How do you get 28? The difference. Exactly. So 789 minus 761 is 28 millimeters of mercury because it's 28 torr. So does that seem like a reasonable question? Is that kind of a bizarre one that once you see what they're asking, it's an easy one? Is it hard at first, easy once you see what they're actually asking? Yep, exactly. So the gauge would reach 28, exactly. Yep, just need to remember what a torr is. Perfect. Okay, so as is my favorite thing to do, oh, you're very welcome. My job satisfaction comes with messing with you, so I'm gonna mess with you over a time period. So if you need a screenshot, do that now because it's gonna click over in a second here. Oh. Dang it, you stole my thunder again. So the question is, what happens if we open this? Gas will flow out? No, don't be sorry. And flow back. So let me ask you a different one. No, and by the way, your questions are awesome and you have to keep asking them. I love that you ask them. I'm just pretending that I thought of it. The gauge pressure would drop to 0. The height difference would be nil. Okay, so here's my question to you. Let's say we didn't open it and it still dropped. How would you explain it? Still a closed system somehow. Yeah, if this height dropped here, but this remained closed, how could you explain such behavior? Chemical reaction, that's one. Something's leaking out, possibly. Pressure drop, what can cause the pressure to drop if you believe in PV equals nRT? Could be that atmospheric pressure went up. That's one possibility. We increase atmospheric pressure, push it over. Reduce pressure in here by chemical reaction that consumed gas. We lowered the temperature inside the flask. Perfect. PV equals nRT. So in other words, can this tie into chemistry? Yeah, when I was that a private or a public comment? Oh yeah. So can I quote you because that's so awesome? In all these absolutely realistic scenarios they always give you in class, you went upstairs to the top of the mountain in the chemistry building that is 4 miles higher than where you started, because that's realistic. Exactly. So you went up the elevator that happened to go up to the sky. Then pressure and atmosphere would go down, we'd see it go the other way. So, and how many had those totally realistic questions in your physics and chem classes? But yep. Imagine a circular cow. uh, that's full circle. That's it. It's so funny because I used to say that years ago, like when I first started teaching, when the first time I did physics, and I swear to God, I think I heard it from a professor, and I think Coy was in that class because I've heard him say it now. So just circular cow, just some ridiculous thing. Yeah, it's just one of those common physics things. When I hear somebody else say it, it makes me laugh just because, yep, just everything we assume in physics is just assume nothing is messing with my question. Okay, give you about 40 seconds. I do apologize. I usually try to get up and walk around a little bit just to circulate. But for this one, are there a few answers you can throw away right away? So how many want to get rid of a couple things? So see a few answers coming in, that's perfect. So somebody wants to get rid of a B, somebody wants to get rid of a C. Okay. I think the easiest one to get rid of would be C because I need to decide which way it moved. They don't tell me what plus 20 or 2.71 and what 0.31 means, but because it is higher on the right side than left, they're saying it starts at plus 2.71 degree, it probably is going down to a situation where it's still higher on that side. So how can the height difference change? By fluid flowing to the left or fluid flowing to the right? Has it flow to the left? How many agree with this? So I'm going to watch here. Height's going to start here and here. And let's see where it finishes. Yep. So it went up on this side, went down on that side. So it had to flow to the left, not the right. So that at least gets rid of one choice. Would that correspond to the gas value increasing or decreasing? So would that correspond to A, or does that also not work? So if the moles of gas inside the system increased, would the pressure go up or down? N goes up, P would have to go up to correlate it. So can I get rid of that choice as well? So A doesn't work. A is kind of messing up our system here. Okay, how many look at B and just question mark it? Honestly, I don't know what to do with it, so I'm going to just question mark it for now. I'm going to jump to D. I think that one sounds about right because 2.71 minus 0.31, carry the thumb, add the pinky. I get 2.4. So I feel really good. I picked D like I think a lot of us did. And that's pretty much right. D is correct, I think, isn't it? Or is it? What I do wrong when I pick D? Ah, dang math. Units. It's 24 torr because they give it to me in centimeters or millimeters, the height difference. Centimeters. And a torr is actually a millimeter. Dang it. That factor of 10 between milli and centi. Ah, dang them. Would they really do that? Is that really up their alley? Okay. Yeah. In fact, this is highly inspired by something they did do. So a question was posted in chat, and I want to get input from you guys. Why is a torr equal to height? So how is that at all correlated? So anybody want to give a correlation? Why am I using height to explain torr? Okay, so we have the unit. I just flat out memorize the pressure of, if it's 1 atmosphere of pressure, it'll raise it 760 torr because it raises it 760 millimeters, it being mercury. And gauge pressure, exactly. So the gauge pressure is measured for whatever reason in torr via mercury. So what we're basically saying is the height difference here between those two, shoot, didn't mean to do that, meant to do it that way. The height difference between the two sides is a difference in height of mercury. And because gauge pressure depends on height, we now made it a unit. We've avoided a calculation by just saying, like, instead of just saying, what is the atmospheric pressure and calculating every time, they just say, well, screw it. Let's just use the height of the mercury as a unit. As the pressure changes, the height changes. And exactly. And as Imana said, the density of the mercury is uniform. It doesn't change. It's not different at any point. And gravity, as long as we're not racing up to the moon in the middle of our experiment, gravity doesn't change either. So the pressure is only going to change with the height difference. Or if you will, a pressure difference is only going to cause a change in height, not a change in density. So we just use it as a unit. So it's basically, it's one of those things that is, makes sense, I guess. I just now have to accept it, that we actually use the height as a unit because the height is directly related to the pressure difference. Okay, so B is the right answer. What is entropy? I probably should know this. Now I'm a little chem confused. Chaos, randomness, disorder. If the volume of the system gets smaller, is the gas able to spread out and be more random, or is it being forced into a smaller region and has become more ordered? It's more compressed, which means it's getting more liquid-like, more ordered. So could we easily have, instead of calling it entropy, could we have called it instead volume? The volume decreased, put the gas in smaller space, it's more ordered. So here's what I believe, and I actually want to go into a little test-taking philosophy, but if you start thinking like a test writer, you're going to end up getting such better results because of the following. If you were to turn this question in originally with the word volume, would it have made it a little too easy to pick B and you wouldn't have been able to trick people with this answer? So you want to trick people because you're mean. So do you change the wording just a little bit, change from an obvious thing to a little less obvious one? Editing of a passage when they do that comes into place like that. When it's a random word, it probably is replacing something that would have been too obvious. So looking at this, did they catch 36 people because of that centimeter millimeter? It is evil. Okay, so the question is, how did the volume decrease? The volume of what? So when we say the volume decreased, what volume are we talking about? Volume of the system, exactly. So the volume inside this closed system here, which do you agree? Guess who sucked in kindergarten at coloring inside the lines? I never thought it'd haunt me. So signing my name, I should have paid more attention in finger painting. Drawing inside the lines, I should have paid more attention so I don't screw up these. Ah, ding, 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 yes. Yes, no question mark allowed in that. So what it was, I got a response in capital letters because the mercury moved to the left. Exactly, the mercury moved to the left. This height went up and it squeezed it into a smaller region. Exactly. So is that a case when you visualize it, it's like, ah, now I get it. Easy, I see it. But it's seeing that damn thing and it's recognizing it. And what is beautiful about this test is a lot of times it's the simple things that once you get those mastered, it works better. Okay, free to move on this one? Entropy is sort of synonymous with volume. So what's meant by that is the gas system, if you compress a gas into a very small space, it doesn't have a lot of spot to move around. So there's a correlation, and so not synonymous, but correlated, that if I reduce the volume, give it a smaller space, they can't move around as much, they're less chaotic. They're forced to be in a smaller region. So if you have a messy room, where is it messier? A small room or a big room? I know it's a weird question, but the bigger your room, the more you can spread out and make your mess. If you're in a small room, you can only spread out and make the mess so much because you just don't have any room to make it. So entropy increases as we expand something. As it gets bigger and bigger and bigger, molecules are free to move to a greater area, greater region, greater volume. So therefore, they're going to be more chaotic. Oh, entropy can always go up and down. Delta S, otherwise delta S would always equal 0. So the universe, that's true. That's one of the laws of thermodynamics. The entire universe entropy is always increasing. But entropy of the system, not the surroundings, entropy of the gas. So entropy of the system has decreased because the volume of the system has decreased. Okay, moving on, next question. I'll give you about 45 seconds on this one. Okay, sorry about that. I was getting something for the house pet. Okay, so for this one, before I do anything, so a little bit hard to visualize this because that's pretty deep, but you ever seen those big oil, like just storage units? Have you ever driven by a refinery and seen just one of those massive oil tanks? Usually there's a ladder on the side. Or you ever seen a silo? Maybe a silo full of oil, full of water. So you fill it up, and if you swam to the bottom of the silo, fill with oil as opposed to fill with water, how much pressure would you feel? And that's what it's getting at. So oil is more dense or less dense? Oil is less dense. So therefore, if you wanted to get the exact same pressure, would you need more or less oil than water to make this work out? More, perfect. So if it's less dense, you need more of it to get the same overall value. So mathematically, I'll make it make sense, but I hope that seems reasonable. That if you were 12 meters down, and it looks like a test tube, which good luck imagining I guess a 20-meter tall test tube. But you'd have to have more oil because it's less dense. So it would have to be more than 12 for it to be equal. So 12 at 1.05, if it's only 0.9, you'd have to have more of it. So how many agree you cannot have A or B? It's got to be more than 12, so it's got to be either C or D. But at this point, is it a math question? Occasionally physics will be that. Can I have some math involved? Have to. So here's what we're going to have. Gauge pressure, rho GH, is the pressure you're going to feel at the bottom in addition to atmosphere. Atmosphere is the same for both. So we have, so setting the gauge pressures equal, I'm going to have rho of this seawater, G, H of the seawater, rho of oil, G. What cancels? Gravity. So if I had a couple ice water and I went to the moon, it's going to float the same because gravity ends up canceling when we do these things. Just random cool little fact. So rho H equals rho H, perfect. And I'm solving for the depth in oil. So I'm solving for that number right there. I actually wouldn't freeze as much as it would evaporate away to space. So if it froze for a brief moment, it would sublime. So, but you do bring up a good point. I'm going to stop doing experiments on the moon then. I'm going to solve for H of the oil, which equals H of the water, and then divide each side by H oil. So let's just double check. Bigger number or smaller number. So this number is greater than 1 times 12 is going to be a number bigger than 12. We're set. Going to plug in the densities. How many, like me, dislike dots in your equation? How many despise the dots and are okay moving it over to make it that? So this extra step right here, is that okay just for my psych, my good mental health in doing this? Yeah, and did it work? So Elton, you plugged and chugged. Did you plug and chug to a happy place? Yeah, it's amazing how this thing works out. A lot of times, number of questions on the MCAT, if you match the units and numbers work out, you've probably done something right. Okay, 5 goes into 105 21 times, 18 times into 90. Is there any common denominator for 21 and 18? Perfect, 3, exactly. So 7 over 6. And 7 is prime, so we're kind of stuck. What about 12 and 6? Perfect. 6 goes into 12 2 times. 2 times 7, 14. Dang, that ended up not being so bad. So how many would agree that the math worked out much better than I thought it was going to work out? An honest answer, how many quit and just took an educated guess on the math? Admittedly, that's where I would be. So kind of the way it worked, but hopefully this seems okay. Yeah, and just the truth of the matter is, as much as I'm trying to tell you, there aren't very many calculations on the MCAT, there are some, and we do have to prepare for it. So you had faith it would work out. Perfect. I don't know where you saw the numbers because 1.05 and 0.9 didn't give me any hint that it would work. I thought it was going to be ugly, but lo and behold, yeah. And it does seem harsh, but then I spin it around on you. When I lied on my lab reports when I was an undergrad and came up with numbers, isn't that a more realistic number if you're going to lie on your lab report than this one? If you're making up data. So there is that factor too. So I argue back and forth. Yeah, see, that's the thing. If you tried to solve for this number first and then divide by things, you can get kind of lost because you start rounding stuff. There you go. I totally agree with that. Okay, moving forward then. That's gauge pressure. Archimedes' principle has to do with what happens when we put something into a tank of water. So if you had a bathtub, they love this example, but let's say you fill the bathtub up to the very brim, right up to the top, and then climbed in. What would happen? Your bathtub's filled to the very top. You climb in. Oh, yeah, sorry about that. So let me go back. Screenshot reference. Oh, crud. Sorry. It's going to take a second to pop up. I'm so sorry about that. I didn't give you your countdown. My apologies. Okay, be ready to screenshot fast because I might be turbo thumbing it, and I sincerely apologize for that. Once you see the scoring grid pop up. Okay. So sorry. So did you get it this time? I so apologize for that. I didn't mean to turbo you like that. Okay. So you climb in the bathtub, the water goes out. How much water? The same mass as you or the same volume as you? Volume, perfect. We displace by volume, absolutely important to know. So next question, if I go into a tank of water, then I'm displacing the volume, I'm pushing the water out of the way. Does water want to be pushed out of the way? Not really. It's going to fight back to try to get that position. So if water pushes its way back in, is that going to push me back up? Hence the buoyant force, exactly. Good way to think about the buoyant force. Does a buoyant force exist before I step into that tank of water? Is there any buoyant force if you have no object? No. Is there any normal force if you don't stand on a block, if you don't stand on a slab, you don't stand on a scale? Nope. Which means just like normal force, just like tension, buoyant force is a reactionary force. It does not exist until you do something. So the buoyant force then is going to depend on what you do to it. The more you go into it, the more volume you put into it, the more you're going to displace, and the greater the buoyant force that's going to push back on you. Is it easier to displace mercury or water? Easier to displace water. So therefore, is it safe to say the density of the medium should also come into play with the buoyant force? Sure. It ends up, the buoyant force is simply the weight of the volume you displace, the weight of the medium you displace. So if I displace 1 liter of water, the buoyant force is the weight of 1 liter of water. So I want to put that equation up there, but I also want to say what we can do in advance, which is going to be very helpful. And real quickly, let me just point out, does this look an awful lot like gauge pressure? Does it look like I'm losing my mind and writing the same equation when I crossed up a V and an H? Now, I won't verify whether the mind is being lost or not, but I will say that is actually the equation. Let's make sure this works out. We said the buoyant force is the weight of displaced fluid. What are the units of density? That's a rho, by the way, not a terrible P like it looks like. Mass per volume times volume is just mass. Mass times G, mg is the buoyant force. The density of the medium, the volume displaced. How much you push out of the way will be the weight of displaced fluid. Okay, big picture. If I put a ball into a tank, I'm going to tell you can do a couple of things. It could float, it could sink, or it could hover in the middle. Hovers in the middle, it's the same density, that's boring. I'm going to ignore that one. But if it's a floater or a sinker, I want to do the math on it. So if this object were to float, tell me the things you know at face value. Is the ball more dense or less dense than the medium it's in? Less dense. And is it fully submerged or partially submerged? Partially submerged, which means the volume of fluid I've displaced is less than the actual volume of the object. So two things that I know. I know it is less displaced than its actual whole volume because some is still exposed, and the density of the object is less than the density of the medium. How many agree these are observations? These are things that I just know because I live. I've seen this. Okay, with that in mind, I want to draw a free body diagram. There's two forces acting on this object. There is the weight down and the buoyant force up, the weight of what I displaced, rho vg. Okay, mass per volume times volume is just mass times g. So I've written it different than here because I like coupling it together, mass per volume times volume, so I know it's mass to displaced medium. And then mg, the weight of the water, which I'm going to write in the same form. So, I'm going to go in a different direction. I'm going to just totally agree. That is the dumbest question ever, to ask for something that's totally valid and can be tested and is fair game and everybody should know. Yep, exactly. It would just hover. It would hover here. Maybe it would hover here, but it would be below the surface, not necessarily touching the bottom. Not a dumb question at all. Perfectly valid question, because I said float, sink, and I ignored hover. Hover is still fair game. It's going to go right in the middle. So whether it's hovering here, here, or here, but hovering means it's going to stay there. Exactly. So when I put it in there, it would just hover wherever I put it. So does that make sense? And sorry to be, I don't mean to be kind of jerkish like that, but whenever I see somebody qualify it with a dumb, like this is a dumb question or something, they're just not. They're actually really good questions. Oh, yeah, we don't play with toys, Elton. You need to just let that go, seriously. So you mean when you were playing with a science experiment? That's what you meant to say. So I would appreciate you not using the T word anymore. Okay, if it floats, what's true? Is it moving up, moving down, or just staying perfectly where it is? Yep, ball of water would just hover there, or a ball of equal material, gelatin, or the same thing. It's just going to stay put. Yes, by all means. So I'm answering a yes/no question in the chat box. Okay, so that would mean the force up equals a force down, because is it at rest and staying at rest? Object at rest stays at rest, meaning the force up equals force down because it experiences no net force. So I'm going to take the liberty of setting these two equal to each other. Weight equals buoyant force, so rho vg equals rho vg. What cancels? Can do it on the moon. Rho v equals rho v. I'm going to isolate so all the densities are on one side, all the volumes on the other. I'm going to come up with this relationship. This is going to be my shortcut. For an object that floats, instead of setting up the picture and the math every time, I'm going to go to this. The relative density, the density of the object over the density of the medium, which how many have learned if the medium has to be water, density of the object divided by density of water is called specific gravity. Is that a term you've ever heard before? Specific gravity of something? Density of the object or density of the material divided by density of water? They love that question on the MCAT because it is unitless and it takes away a little bit of the arduous math so that they can make a more conceptual question. So hopefully that seems okay. So specific gravity, density of the object divided by density of water. So let me see if this makes sense. Do you float higher in salt water or distilled water? Why salt water? Absolutely correct. Why? More dense. Perfect. As the density of the medium goes up, the number gets bigger, this number gets smaller, which means the volume of the object doesn't change, so the amount displaced has become less, you're less submerged. Yep, exactly. So was that on every single question? Or every single homework, midterm and all that, that floats higher in saltwater versus freshwater? They love that for whatever reason. Kind of a cool little thing as well. I don't know if any of you watched the Olympics, if you were old enough to watch in 2008, but the China Olympics were probably the greatest swimming event in Olympic history because everybody was setting world records. I mean, it was amazing. So what is one of the things they did in those Olympics midway to figure out what the heck's going on? Yep, exactly. That whole Dead Sea floating example they love to give, but saltier it is, the higher you float. But what happened, if anybody knows this, those Olympics, just records were set left and right in the swimming pool. What was one of the very first things they did? They tested the salinity of the water, exactly. They also looked to see if there was any sort of underwater draft, like a vent that was blowing water one way, that if they got in a streamline that would push them along. It wasn't any of those things. It ends up that us and the Australians were cheating with our swimsuits. Our swimsuits had these like basically dimples in it, so it would change our buoyancy a little bit. It would change our surface tension, I should say. But it ends up, it wasn't illegal at the time, it became illegal. So it was something called the laser suit. So it was a swimsuit that if you were from a country that could afford a really fancy suit, you're going to swim faster. Technology that wasn't yet banned. It's since been banned. So now it looks like, again, a European vacation where everybody's in a Speedo. Back then, everybody had these full suits that would cause the body to lift up in the front more than the back, so you'd get your legs more in the water for power. Yep, exactly. We always figure out, ooh, that wasn't a good idea after something blows up. So at any rate, but yeah, they tested the salinity of the water and it ended up, it was right at the legal limit. But yeah, for something to be a world record, has to have a certain salinity limit in the pool. So hopefully these things seem okay. If the object sinks, here's what's going to happen. There's still a buoyant force, but is it heavier or lighter when I lift an object underwater than out of water? Why is it lighter? Is it truly lighter or it feels lighter? It feels lighter because of the buoyant force. So let's say you have to move. Let's say you got to move from one apartment to another, just kind of life as a college student, for those who are college students still, which I think is one of you, two of you. But if you have to move, would this work out? Could you seal off all your window seals, all your doors, make it airtight with like duct tape, ductile tape, something, and could you fill your apartment with water to make it everything lighter, like your big screen TV, which normally heavy, light as a feather. Pick it up in the water, it's lighter. Pick up your couch. Would it be much easier to flood your apartment to move everything? Like all your books, light as can be underwater. Because life hacks, very useful life hacks. I'm glad that you see this as a genius maneuver. But one of the things they talked about on an MCAT years ago that was really cool that sort of brought this to light, they're talking about the building of the pyramids. And when I say pyramids, I think everybody immediately thinks of Egyptian pyramids. But this is kind of a cultural question. Bear with me on this. But how many come from a culture where you stack blocks as a kid? There's a method to my madness in asking this. So how many come from a culture where you stack blocks? One yes, two yeses, three yes, of course. How I still stack them. Excellent point. So the beautiful thing here is, would you agree we represent a pretty good cross-section of ethnicities, cultures, and all that? Yet, do we all stack blocks? Is that kind of what you do as a kid? Doesn't matter what flavor you are, you stack things. That's what we do. Grow up and then you stack and make tall buildings. Everybody tries to build skyscrapers. It's just built into our DNA for whatever reason. Okay, so the pyramids, there has pretty much every country taken a crack at stacking blocks as a grown-up and making some sort of pyramid or tall structure. Egypt has not cornered the market on pyramids. They're all over the world. And so what this one was a South American pyramid. And what they theorized was they made the bricks in the water, they moved them through the water, through these chutes, lifted them through water, and then put them in place, and then let the water drain out. Why would they move them through water? What was the reasoning behind that? Why less work? You're absolutely right. Why less? A little less friction, probably. True, you aren't scraping solid on solid. That helps. And they're lighter. Buoyant force. Buoyant force is going to lift some of it, so you don't have to do as much of the effort to lift the block. So is that the same idea? Did these pyramid builders from thousands of years ago steal my idea about how to move your apartment? No, they're not geniuses. They copied me, damn it. My idea. Yeah, so you have to have some drainage system. And that's what they point to. All these pyramids in at least in South America where they're talking about, all have a built-in water drainage system for the rain and everything else. But yeah, it's going to be saturated with water, and they build up all the layers, and they eventually had to drain it out. But there's river soot on the inside and outside of the pyramid, all the way up to the top. So they're pretty sure this is how they did it. Oh yeah, people are much smarter because everything we take for granted today was something somebody discovered years ago. So, yep, we do think we've cornered the market on smart, and we haven't. Yeah, exactly. How many have learned that? That water gymnastics is actually a lot healthier for you because you're not stressing your joints. But if you stay in water too long, your body will adapt, and there are some other issues. So I don't think it's a big deal, but we are meant to be on land, but yeah, less stress doing that. Okay, couple things going on here. Why do I have 3 forces here? Why is there a third arrow? There is a buoyant force, by all means. One of these is buoyant because buoyant is pointing up. But what else is there when it's resting on the bottom? Ah, the normal force, exactly. There's still a weight, there's still a buoyant force, but now there's a normal force. The normal force is defined as your apparent weight. Meaning when I stand on a scale, is it reading my weight or is it reading the normal force needed to offset my weight? It's reading the normal force. It's what you appear to weigh. So when you weigh yourself in air, there is no notable buoyant force. So you pretty much get a true weight. But if you weigh yourself underwater, is that the best way to lose weight? If you want to lose weight fast, weigh yourself underwater. What happens? The normal force becomes less because the buoyant force is pushing you up a little bit. Oh, who cares about the scale? Yeah, break the scale, throw it out. That is one way to solve it. Take the batteries out, you can't read it. But buoyant force is referred to as apparent weight loss. I want to be careful saying that. So weight is just normal force. Actually, apparent weight is the normal force that we're reading on the scale. So my weight down is equal and opposite to the normal force of the scale pushing up. So I don't want to say it is, I want to say it is equal in magnitude to the normal force. So without any buoyant force, if you're in a vacuum, the weight down is equal in magnitude to the normal force up. So the normal force is the weight in terms of scalar quantities, in terms of the numerical value. So they're numerically the same. So when we stand on a scale, it reads our normal force. Specific gravity is mentioned before, density of the object over density of the water. So I can't set them equal to one another anymore because they're not equal. So instead, I'm going to do weight over buoyant force. Yeah. Okay, your apparent weight is the normal force. It's just, this is what it is to a physicist. This is a layman's term. So they're the same thing. So if I say I stand on a scale and I weigh 71 kilograms, that's because the normal force reads 71. So apparently I'm 71. I'm making a leap of faith that this equals this. So what I appear to weigh is the normal force. So it's just a different way of saying the same thing. So if you want to formally say something, this is a less than formal way to say it. No, they're equal. So if it is sunken and stationary, so let's look at this scenario. Floats on top, hovers in the middle, or sinks to the bottom. When it sinks to the bottom and hits the bottom, it's stuck. It's not moving. Can't go through the bottom. So at that point, you agree, is it at rest? When the object hits the bottom of the pool, bottom of the tank, is it moving or is it just sitting there? Just sitting there. So it is at rest. So what do we know about an object at rest? It has a net force or no net force? Net force is 0. So all the forces down, which is the weight, must equal all the forces up, which are the buoyant force and normal force combined. the sum of the buoyant force and normal force up must equal the weight of the object down because there is no net motion. So the apparent weight, what you appear to weigh, is your weight minus the apparent weight loss. And so this really comes down to just word choice that physicists are using. So normally, let's say my weight is normally 60 kilograms. If I appear to weigh 40, then the buoyant force must have taken away 20. That's all we're saying, is that the sum of these two equal this. So normally in air, my normal force and weight are synonymous numerically. So after telling you don't use the word synonymous, I totally just used it. Oops. But they correlate. Uh-oh, could somebody let Stephanie in? I don't know how she got booted. So sorry, oh, okay, thanks for letting her in after I think we vote kicked her. Sorry about that. So welcome back, Stephanie. Oh, you vote kicked yourself. Or, okay. So weight to buoyant force ratio, I'm just gonna set this up as 1 over the other. Density of the object, volume of the object, G, that's a weight. Why is it volume of the object for the buoyant force? Why am I including that as volume, the volume there? They're the same, it is fully submerged, exactly. Because it is fully submerged, if it's 1 liter, it displaces 1 liter. So gravity cancels as always, but so does the volume of the object. Have a good night. You're welcome. See you tomorrow, probably in office hours. Okay, so I have weight to buoyant force ratio equals relative density. That is my shortcut equation right here. So here's what I'm going to ask you to do. We're gonna apply this, but I want you, if you get anything on buoyant force, anything on Archimedes principle or an object in a fluid, I want you to answer the question first, is it a floater or a sinker? If it's a floater, the relative density is the volume displaced over volume object, or percent submerged, if you will. And if it's a sunken one, then the relative density equals the weight to buoyant force ratio. So screenshot, if you will, I'm about to click over, and we'll apply this. So if you have questions, I hope a question will solve a question. Okay, so clicking in 3, 2, 1. Okay, so what is specific gravity for an object that weighs 40 newtons in air and 24 newtons in water? Okay, is this a floater or a sinker? Why do you say it's a sinker? You're absolutely right. What makes you conclude this? So everybody's saying it? Because it weighs something. Perfect. If you float, you're floating, quote unquote, weightless. Okay, so perfect. So we have that. So that means I need to set up the relationship where weight over buoyant force ratio equals relative density. So for an object that sinks, I'm going to start with this relationship. The weight over buoyant force equals density of the object over density of the medium. Luckily, it's asking for specific gravity. So that is just specific gravity. So I just need to get weight and buoyant force. So what is the weight? The weight is 40. What you weigh in air is pretty much what it is. And then buoyant force I'm going to say is 24. Is that correct? Or did I screw that one up? TGL. Screwed it up. What is 24? Is 24 the buoyant force or the normal force? Dang it. You're right. So I messed that one up. Normal force equals 24. So what does the buoyant force have to equal? 16. Dang it. So it's not 24, it's 16. So now I feel a little bit better. 40 over 16, I don't care about units because it's unitless. So newtons over newtons, I'm going to ignore it. 40 over 16 reduces to 10 over 4, 5 over 2, 2.5. is this actually pretty easy if you set it up like this to start out with. It is a sinker, so I'm going to start out with my sinking relationship. Okay, if it were a floater, how do I know this one is floating? How do I know it's a floater relationship? It says it in the question. And 10% exposed, so I know it's exposed, so it's not fully submerged, not fully engulfed in it, and it says floating. So for a floater, relative density equals what? So for a sinker, weight to buoyant force equals relative density, but for something that's floating, the percent submerged, the volume of the submerged divided by volume of the object, percent submerged equals. So if it's 10% exposed, it's 90% submerged. So setting it up, the percent submerged, the volume submerged divided by volume of the object, percent submerged equals relative densities. So in this case, I do need to solve for density. Percent submerged is 90. So 0.9, 90% equals density of the object over 0.8. Multiply each side by 0.8. Whew, I don't like dots. So can I ignore the dots for now and say 9 times 8 equals 72 and then add a dot into it? Sure. So we end up with 0.72. Why does this suddenly have units where it didn't have units up here? Difference is this question asks for density, which has units. Oops, sorry, circle along density. This one asks for density. This one asks for specific gravity, which has no units because they cancel, just like you said. Perfect. Does this seem okay? Does this, I don't want to call it a shortcut as much as it is just taking advantage of how we've organized things. So with that in mind, I want to give you 3 questions. So screenshot, if you will. I'm about to click over in 3, 2, 1. You're on. What is the equation for a floater? Percent submerged equals density of the object over density medium. So if we want it to float really, really high, then I want it to be a very large or small amount submerged. I want a small amount submerged, which means I want a small density of object and a large density for the medium. How many agree with that? The denser the medium, the higher you float. So can I compare A to B and C to D and at least get rid of a choice straight out of the gate? And all of you are getting the right answer, so I apologize for going slow methodically. But how many agree that these are almost the same density. This is barely going to float. This one, how many would agree A is bad, B is a little bit better answer for now? So A is going to go out, B is going to be a little bit better. And how many agree same thing with C? They're the same object, but because it's a denser medium, it's going to float higher. So can C get eliminated by comparing to D? Okay, so A and B have the same density, so they're out. And then in comparing B, their density is so close, it's not going to work out well. How many agree D is my best answer? Same object, but much more dense medium, higher it's going to float. Weird question, but what do these words mean? They actually have expected people to know these. Water, H2O, density equals 1.00. What exactly is saline and what is brine? Saline is saltwater, brine is saltwater. Which is which? It means the salinity or the molarity of the ocean. This is saturated salt. So please tell me, when you look at these words, you start thinking things like hypertonic, hypotonic, isotonic. So let me see what happens. When you go into the ocean and you're in there for a while, how many notice you don't really get as shriveled or waterlogged as if you went into pickling solution? Why you're in pickling solution, I don't know. But what happens in a pickling solution? So pickling, you put a cucumber into brine, what happens? A little bit of salt might go into the cucumber, but does it literally suck water out of the cucumber? Water leaves, shrivels up. What happens when you put a cucumber into distilled water then? What should happen over time? It should swell up. It would start sucking up the water. Water would go into the system. And then if you put a cucumber, well, okay, this is going to be a bad example. Put it in the ocean, it's still going to shrivel up, just not as much as brine solution. But hopefully this seems okay then. The terms, water, density 1, saline about 1.02-ish, and brine around 1.06. Just random numbers to add to your collection of useless numbers that you will forget day after the MCAT. But know the terms. Pure water, salt water like the ocean, saturated salt water like pickling juice. Okay. Gonna click. 3, 2, 1. Same question, but now for a sinker. To sink the fastest, would you expect it to be heavy with low buoyant force or light with a lot of buoyant force? Which is going to sink really fast? Heavy with a low buoyant force. How many agree that picture would equal something that's going to sink really quickly? Which means we want the weight to buoyant force ratio to be very large. So we want density of the object over density of the medium to also be very large. How many are in agreement with that? We want a highly dense object and a not very dense medium. How many get that intuitively more than anything? What's your worst answer? What's the first answer and easiest one to eliminate? D, exactly. So it has to be greater than 1, otherwise it'll just hover. So D is out. And then is there any answer I can get rid of with relatively little math? What is the most pain-free one to eliminate at this point? Exactly, C. Why C? Same object, but more dense than medium, it's going to slow it down. So we want the largest weight to point force ratio, as we mentioned. So we want the largest density of object divided by the smallest density to medium. Choice C is out because A beats that. So here's the tricky one. How do I know that mathematically? I mean, how many know that that's true? So a couple different ways to solve this. I'm trying to figure out whether 1.3 over 0.8 is greater than or less than 1.5 over 1.0. Few ways to go through this. Just want to revisit a certain math trick you may have done. How many learned the cross multiplying trick? How many learned that you do this? 1.3 times 1 and compare that to 1.5 times 0.8. How many have done that one? So 1.3 times 1 is just 1.3. 1.5 is 3 halves. This is 4/5. That's going to equal 3 times 4, 12, over 2 times 5, 10. So 1.2. Because 1.3 is higher than 1.2, 1.3 over 0.8 is higher than 1.5 over 1.0. How many remember that as a math thing you've done in the past? That is one useful way. The other way, in the way I think I would recommend it, this is nice if you can find a number to compare it to. That's great. If you're good at numbers, this is pretty straightforward. Cross multiplying, that's another method. But I like looking at the leftover method. I like seeing this as 0.8 over 0.8 plus 0.5 over 0.8. I like looking at the other one as 1.0 over 1.0 plus 0.5 over 1.0. That's one and that's one they canceled. So which remainder is bigger, 0.5 over 0.8 or 0.5 over 1.0? Left one's bigger, perfect. So any way you cut it, then that's your bigger answer. Common number, common denominator, common numerator to compare to. That's one easy way to do it. Cross multiplying, that's another way to do it. And then look at the remainder. That's another way to do it. You're going to get a little bit of math on your test. It's not a bad idea to just master a few of the math tricks. But I mean, you pick the one that works for you. And I would recommend on homework trying all three. And will you decide very quickly which one you like and don't like? In fact, how many have already made that decision? So how many are good at intermediate numbers, finding a common denominator or common numerator to compare with? That's one way. How many like the multiply across because it's uniform? Might take a little more time, but it's just comfortable. I use it. And how many like the remainder method? Perfect. Pick your method, master it. I'm a remainder person, honestly. I think this is the easiest one for me. Okay, one more question. So screenshot away, 3, 2, 1. Okay, so for this one, perfect. Answer's starting to show up. So what I'm uncertain of in this one is, relatively speaking, which is more dense, CCl4 or water? So yeah, I'm not really sure how to figure that one out. So where is it floating higher? Is it floating higher in water or floating higher in CCl4? Ah, higher in CCl4 because it's 75% submerged, it's 25% floating. 50% submerged means 50% floating in CCl4. So it floats higher in CCl4. So that means CCl4 should be denser than water or less dense than water. Denser than water, so C is the first one I end up eliminating. That one's out. Okay, are you getting B because you're just tossing numbers in there? Because I gotta be completely honest, first time I ever saw this question, that's exactly what I did. Crap, don't know what to do. It's either 75 over 50 or 50 over 75. They're both there. So, yep, kind of what we have to do. Here's how you solve it formally. Okay, so with that in mind, here are the two things I know. What specific gravity is density of the object divided by density of water, or density of CCl4 over density of water if I'm going for specific gravity CCl4. But here's what they tell me. 50% submerged in CCl4, so density of the object over density CCl4, 0.5, 50%. Density of the object over density of water, 75% submerged, so 75. They each have density of the object, so I'm going to move this over here, multiply both sides, and put it into this. And then I'm simply going to set this equal to this. Okay, so I'm ultimately looking for density of CCl4 divided by density of water. So I'm going to divide this side by density of water and then move the 0.5 over there. So in doing that, what is 75 over 50? 1.5. Perfect, 1.50. Dang, I lucked out because I thought something was right, and lo and behold, it was. Is that okay to do on the MCAT? Not be 100% sure, but use logic you normally do and have it work out? Yeah, and 1 divided by 0.67, if you know that these are inverses. So if you recognize that that's 3/2 and that's 2/3, then you know something's going on there, that there's probably some number. C is one number less than 1. Exactly. So are you thinking, your logic, that it's a number less than 1, it's an error, but it's an error somebody might make computationally, and the test writer probably knew that somebody would make a computational error? So if it's 2 over 3 is an error, then 3 over 2 is probably the valid one. Weird as it may be, that is great logic. That's going to help you as a doctor, or simply help you to get into doctor school by giving you a kick-ass MCAT score. It's great test taking. Use it by all means on all your standardized tests. Probably don't want to tell a patient this. So yeah, I don't know anything. I just know how to, something's wrong, that's probably the inverse is right. But spot on. Thinking like a test maker, exactly. The more you do that, the better you do. Okay, moving onward and upward then. So far so good. We're done with objects.
Todd, sorry, I just have a question on the last slide. If you can't go back, it's totally okay. Oh, okay. But I have an issue with getting, after that step, totally fine with that. It's that next step that I have issues getting to, where you put the, let me see, it's like the density of CCl4 over water equals 0.75 over 0.5.
Yeah. Well, okay, so the only thing I know, I have 3 terms in here and 3 terms here. I have one common term for both of them.
Mm-hmm.
So somehow, some way, I want to make this and this cancel out. So I could, if I wanted to, just divide one by another. But instead I said, taking an extra step, I'm going to say, well, let's isolate this by moving that over here, isolate this by moving it over.
Right, got that part.
And then setting those two equal to one another. And then the step that I was kind of lazy about, I divided both sides by density of water and both sides by 0.5.
I see.
So
Okay.
with that over that, which is what happens in the next step.
Okay, I see. Thank you.
You're welcome. So, frozen up. Oh, perfect. Screen's about to move up. Okay. Voices, we mentioned this, how a straw works. So you need to teach me some things based on what we started the lecture with. Where does fluid move the fastest? The edges or the middle? Perfect. Fast in the middle, slow on the edges. You have a boundary layer, you have friction. Okay, seems reasonable. So is there a difference between saying the speed of the fluid and the volume flow rate? Are they actually two separate terms when they talk about it? So ultimately, we're going to conclude is the average speed times the cross-sectional area equals the volume that is moving. Meaning, the average speed of all these different particles times the cross-sectional area they're moving across tells me how much fluid is moving. So this is meters cubed per second. This is meters squared per area, meters per second. So speed is how fast the individual particles are moving, and volume is how much fluid is moving. So does a river have a large or small Q? Does a river move water fast or lots of water? River moves lots. Okay. What about a pressure hose? Pressure hose will blast you. It'll hurt. It'll sting because the water molecules are moving very fast. But it stings on your entire body or just a small spot where it's hitting because it's not a lot of water. So put your thumb over the edge of the nozzle on your hose. It'll shoot faster, but the same amount of water is coming out of your hose. So hopefully that seems okay. Is that fast moving water and lots of water moving are two different terms. So the speed and the volume flow rate. Okay, so with that in mind, the equation. The volume flow rate, how much it moves, depends on, as we mentioned, pressure difference. Things flow from high pressure to low pressure. Also depends on viscosity. Wow, that thing came in slow. Depends on length, as we mentioned. Longer pipes, the longer the pipe, the more the gradient is spread out, the more friction it experiences. So it flows more slowly. And then bigger area, pi r squared. But again, it is or is not pi r squared. I can't remember. I've already forgotten from the start of the lecture. Squared root to the fourth. Oh no, you've forgotten her. Is my sound out? To the fourth. Perfect. Why to the fourth? Like we mentioned before, it's physics, it's weird. I'll go with that, but I was going to go with the area is true, but also the bigger the pipe, the greater the average speed. So how's that? I'm also missing an 8. 4 variables. 1, 2, 3, 4. I'm going to look at those in a second. Yep, exactly. The speed increases in the middle as it gets wider. There's also something called the continuity equation, the funneling effect. You've seen this in traffic. How many have ever noticed when 2 lanes go down to 1, it's really slow going in, but once the lanes merge, you move faster. But all the cars going in equal all the cars going out. So A1, V1, because the total going in equals total coming out, A1, V1 equals A2, V2. So I want to apply this in 2 ways. Method number 1, how many have ever noticed you go to downtown anywhere, pick a city, any city, downtown always feels windier? How many have ever noticed the wind is blowing much faster downtown than it is out in the plains outside of downtown? Have any of you ever noticed this? Every city has a windy downtown. Those pesky buildings. So A, are the buildings farting, giving off gas, or are they forming wind tunnels, as you're talking about? Air can or cannot go through the building itself, or does it have to go around the building? Has to go around the building, so all the air that normally would go here is being blocked, so it has to funnel in. So air goes down, speed goes up. Yep, it's not farting buildings. That was a terrible analogy. I apologize for that, but hopefully it seems reasonable. How many have ever been to the mountains and would agree the mountains always feel windier than it does down below? I mean, would anybody agree you can always hear the wind whistling through the trees when you're at the top of the mountain? Because all the wind coming across gets scrunched. Okay, not that I just read that in chat. So, but perfect.